today I want to talk about implicit differentiation, and then hopefully time will permit, and then we'll be able to use this as an application of implicit differentiation. We're going to discuss how to find derivative of inverse functions and how to figure out the derivative of the inverse trigonometric functions, inverse sine, inverse cosine, inverse tangent, and so on. Okay, so that's the purpose for today. And that's why I asked you for Friday to rewatch the lecture of Wednesday about chain rule, because implicit differentiation is really just an application of the chain rule. Okay, so let's talk about this. All right, so I was kind of telling you a little bit about the difference between an implicit and an explicit function last time. Let me remind you of this. Okay, so implicit versus explicit functions. So remember, a function is just a relation in which you give me an input, I give you an output. Okay, each input has only one output. That's what a function is. And you can, the way a function is presented to you, there are many ways that a function can be presented to you. Okay, one of those is explicitly, which is when the formula is given to you. Like you see the formula f of x equals something, or y equals something that only has x in it, or whatever the variable is. That's what we mean by an explicit function. Implicit means I'm not giving you the formula, I'm giving you an equation, a relation between the variables x and y. Okay, and you don't know exactly what y equals to, but nevertheless, that will define a function. Okay, so let y equal f of x. So here we say, remember that y is a function of x. And in this case, f of x, this is some formula involving only x. X because it's a variable. If you have f of t, then it's a formula only involving t. When you have something like this, we call that an explicit form of the function. So this is called an explicit form of the function. Okay. However, we may not know the formula, but instead an equation. And in general, I'm going to write the general form of how this looks like. So you can have something like this. Capital F of xy equals c, where c is a constant. Okay, this guy right here is a constant. What I mean by this is just an expression. You can think of it as a function in two variables. This is just an expression, an expression that involves both variables, x and y, okay, equals to some constant. And in general, you can actually put a 0 here because you could put the c over here and then put it together in this expression, okay? But I'm just going to leave it like that. So whenever you have an expression involving x and y, let me say that here. So this is just an expression involving x and y. And it's understood that whenever, the convention is that when you use x and y, it's understood that x is the independent variable and y is the dependent variable, okay? But you could do it the other way around as well. But typically, y is our dependent variable. Okay, so whenever you have something like this, we are in presence of what we call an implicit form. Of y as a function of x. So let me give you an example so you can see. So in fact, let me write down the definition. I'm going to give you an example so you can see. So an equation in x and y defines a function f implicitly. So when will an equation like this define a function f implicitly? Remember, y will be equal to f of x. So every equation always have a graph. What's the graph of an equation? Just put all the points and solve the equation, and they are going to make a graph. For example, think about the equation x squared plus y squared equals 1. It's an equation. What's the graph of this equation? It's a circle. Now, I want you to understand a circle is not a function. Okay? Now, you can think of this as being a function, y as a function of x, if a portion of the graph of this equation coincides with the graph of f. So what's a function? What's one function that we can take from here? The square root of 1 minus x squared, right? So if you solve for y, you move the x squared to the other side, the square root, you're actually going to get two functions, the positive version and the negative version, right? What's the graph of this one? That's just half the circle, right? So if the graph of the function f coincides with part of the graph of the entire equation. The entire equation is the whole circle. A piece of it is a function. As you can see, this is a function. And because the graph of f is part of the graph of this equation, we say that f is defined implicitly by this equation. Okay? The danger here is that the same equation may define several functions. There are two functions that you can define from this equation. Okay? The positive version and also minus the square root of 1 minus x squared. Again, this is just so we have the definition in place, but you really are not going to need it as long as you understand what implicit is. So an equation x and y defines a function f implicitly if the graph of f of x, of y equals f of x, coincides with a portion of the graph of the equation. Okay, and then I guess as a concrete example, we have x squared plus y squared equals 1. If you want, this right here is what we mean by f of x comma y. That's our expression in x and y. And this guy right here is the c from above. Okay, and this is a circle. So this is a circle, and it defines implicitly the function f of x equals square root of 1 minus x squared. And let me stress here, this is the upper half of the circle. And also the function g of x equals negative square root of 1 minus x squared. This is the lower half of the circle. So let me color code this. And then let's put this one in blue. Okay, so basically we have our equation, we have our circle. This is the unit circle. So this is the graph of x squared plus y squared equals to 1, but then a portion of the graph, which is this one over here, that represents the function f. This portion of the graph represents the function g. Do you understand this? So by looking at the definition, these two functions f and g, they are both an implicit version. So they are both defined by this implicit equation, by this equation. Okay? Which one is it that you want to consider? Well, it depends what your interest is. You're going to see in the examples when we look at ellipses and so on later. Okay, so the whole point here is that now typically when you have an implicit definition of a function, it's going to be given to you like this, okay, as an equation instead of just a formula. If I give you this, then that's it. This is an explicit version, okay, while this is an implicit version. Questions? Do you understand this? Okay, so one example, then example number 2. By the way, you understand where those formulas are coming from, right? I'm getting those formulas. You're solving for y. And when you take square root, that's the plus or minus that you obtain. Okay, so as another example, then we can look at this a little bit more silly. So x times y equals to 1. This is an equation. So this is an explicit form. Implicit form, sorry. So this is an implicit form. But, you know, instead of looking at this, what would be the explicit form of this equation?
Y equals 1 over x.
This is y equals 1 over x. We are more comfortable looking at, right? Because we kind of know what this is. This is what we call the explicit form. So if you want to do something with this implicit form of the function, maybe you will be more comfortable writing y as a function of x, and then you work here. Like, for example, say that we want to take the derivative of y. We want to find y prime, and so on. It's easier to do it on this side because we have formulas that will help us to do this. Okay. The problem is, and not always we can do this. Not always you can go from the implicit form to the explicit form. Explicit form, if it's not given to you, in general, it's very hard to find. Okay. Let me give you a less trivial example. So we already saw a circle. In the circle, you can get away because you can also solve for y. That's fine. You get two formulas, but that's okay. But how about if I give you something like this? X squared minus 2y cubed plus 4y equals to 2. It's an equation. Here is your expression involving x and y, right? Equals to a number. And then, you know, this is, of course, an implicit form. So this right here is an implicit form. And let me justify why, just to make sense of this. So notice that here we can consider y as a function of x. How? Remember, all I'm saying here is that you give me an x, and I have to be able to give you a y. Okay, for each x that you give me, I should be able to give you a y. That's what that means. Okay, give me an x value. We put it here, what do we get? We get a cubic function. We get a cubic polynomial, cubic equation in terms of y. You can always solve this equation. There is at least one real solution. You know, we have up to 3 solutions, but 2 of those could be complex. Okay, but when the degree is odd, there is always at least one real solution. So for each x, there is at least one solution to this equation. That's my y. If you have more than one solution, well, just pick one of those, and that's what's going to determine a piece of the graph and not the whole graph. Like in the case of the circle, you give me an x. When you solve for y, there are 2 possible y's that you can get, right? A positive version and a negative version. Whichever you decide to stick with, that's the one. That's what's going to define. Are you talking about the upper half of the lower half of the circle? Okay, that's why we say a piece of the graph and not the whole graph. So certainly y can be considered as a function of x, but this is the implicit form. Can you solve for y here? Can you give me an expression for y? You can try as hard as you can. You're not going to be able to do this. Okay? But nevertheless, there is a function here, y is a function of x, and we are interested in finding what is y prime, what's y double prime, and all of these pieces. Okay? So this is what we want to study now. So this is the implicit form, and then just say it is difficult. I don't want to say it's impossible because, I mean, I don't know how to solve for y here, and I don't think it can be done. I don't want to say it's impossible because maybe, you know, there's a crazy formula that will allow you to do this. But certainly, it's not something as simple as just let's move the x to the other side, or let's take square root and we're done. Okay? For example, if we didn't have this 4y here, then it's easy, right? Move everything to the side, take cube root, and you're good to go. But that 4y then complicates things. So let me just say it's very difficult. So it is difficult to solve for y. To solve for y here. And why do we want to solve for y? This is because, in case that you were wondering, maybe I want to find the explicit form. To find the explicit form. So we have to be able to work from here. Okay, that's the whole point of implicit differentiation. Okay, that's fine. Just work with the equation. Don't work with the formula, but with the equation. Okay. So And another example, since y is a function of x, let us find dy dx. Find dy dx in the above examples. Okay? All right, so, and by this I mean number 2 first, and then we're gonna do 1 and 3 later, okay? So example number 2, we have xy equals to 1. If you wanna find dy dx, well, we can get away easily by just saying, okay, this is the same thing as saying y is 1 over x. So dy dx, or y prime, equals, what is it? What's the derivative of 1 over x?
Negative 1 over x squared.
Negative 1 over x squared. So we managed to do it. Yes? Now, of course, here we rely on the fact that we could solve for y. The question is, what if you can't? Okay? How do you find dy dx if you cannot solve for y first? So this is fine. So now for number 1 or 3, actually, number 1 we could do it. It's just that it's going to be a little bit tedious, so that's why I want to wait. Because if I give you this equation and I ask you to find for y prime dy dx, what you could do is solve for y. You're going to get 2 formulas, but then you need to take 2 derivatives. Okay? Because if I give you the equation, I want to know the whole thing, not just the upper half of the lower half. Okay? And also finding this derivative, you have to deal with the chain rule, there is a square root, could be a little bit painful. Okay? So I'm gonna hold on to that for a second, and then once we discuss implicit differentiation, we're gonna come back and we're going to nicely do it. All right? So I will say here, number 1, which is x squared plus y squared equals 1. This can be done, but it is tedious. Point is that there is a better way. So we will see it soon. So let's wait. Okay? And the whole point is that then when we come to number 3, we are stuck. So we cannot even get away by solving for y. So that's why we need to discuss a new technique. Okay? So number 3 cannot be done as above. So the question is, what do we do? Okay, so what do we do? How do we find y prime? Remember, the goal here is to find the derivative of y, and think about something like this. How do we find y prime? And if you want, don't even look at the whole function, okay? At the whole equation. Let's just look at something like this, y cubed, this expression right here, y cubed. How do we find the derivative of y cubed with respect to x? Okay, what do you mean by power rule? Okay, that's the derivative of x cubed. Yes? Now, you have y cubed. It's a different story. You understand this? So, for example, note. Let's say that we want to find the derivative of y cubed. And let's say, I don't know, let's say that y is the function sine of x. Just remember, y is some function, right? So let's say that's equal to sine of x. So finding the derivative of y cubed is the same thing as finding the derivative of, so what is it? It's the same thing as finding the derivative of sine cube of x. Do you understand this? So remember, when we say that y is a function of x, that means that there could be a formula out there, it's just that we don't know what it is, or we just cannot find it, okay? But y is a function of x. It's just that you don't know what the formula is. So here I'm kind of giving you already a formula. Let's say y is a function sine. You want to find the derivative of y cubed, that's the same thing as finding this derivative. What is this derivative?
3 sine x squared times cosine.
3 sine squared of x times cosine of x. Everybody agree? So let's see. This part right here, let's break this down a little bit. This part right here, let's write it in terms of y. How does it look like in terms of y? In terms of y, how do you write this expression?
3y squared.
3y squared. So that's what you were saying earlier, right? That's not everything. What else do we have? What is this in terms of y? This is y prime. Do you understand this? In other words, when you have y cubed, what is this? This is a composition. Y is a function of x. So this is a composition. What composition? The outside function is the x cubed function, and the inside function is y. For example, in this concrete case, you know what y is, it's sine. But when you don't know what y is, it's still a function. So y is still the inside function. It's your g, the chain rule. Do you understand what I'm saying? So when you take the derivative, you do the derivative of the outside, which is this part right here. Okay, your usual power rule, but then times the derivative of the inside. In this case, it's y prime. What is y prime? Well, I don't know. In this case, we know because y is sine, so we know y prime is cosine. But when you don't know the formula, then y prime is y prime. The same thing that y is y, then y prime is y prime. It's some function. Do you understand what I'm trying to tell you? The point is that when you see this, you have to use the chain rule because there is a composition taking place. Okay? And we're going to take advantage of that to be able to find derivative. Is this clear? So the idea here is, just recognize that y is a function of x, and so when we find derivative, we may use chain rule as needed. In the context of an implicit definition of y, that form of taking derivative is called implicit differentiation. Okay? So when y is defined implicitly, this is called implicit differentiation. Okay, so let's do some examples so you can see the technique. But basically, it's really nothing new. It's just chain rule, but you need to understand that you're not going to be seeing something like this sine cube. Okay, you just see an expression involving y's. Think of y as a function. If you get confused, just put a sign in terms of y, in where y is in your mind, so you know what you need to do. Okay, because it's very easy to just say, oh, 3y squared. Yeah, but remember, times y prime. Okay, this part is what typically students forget. Chain rule. Okay, so let's do some examples. So we already did above. Let me just find, or let me say evaluate. So evaluate. Here, Leibniz notation is kind of nice because the derivative you think of it as an operator, something that you are applying on an expression, and it will give you a result. And the reason why this is good is because it tells you with respect of what variable you're taking the derivative. Okay? You see, derivative with respect of x. So that means that here you don't have an x, you have a y, so chain rule is needed. If I would have written d dy, that's the derivative with respect of y. Y is your independent variable, so in that case it would just be 3y squared. Right? So this makes the difference. Okay, so evaluate. Let's do d dx of y cubed. We don't know what y is, okay? So, of course, here, assume in these examples, assume y is a function of x. I'm not going to tell you a formula. So let's do this one. Let's do this one. Let's do this for examples, okay? Okay, so y is a function of x. So here we want to take the derivative with respect of x. You know, if y is a function of x, then y cubed is also a function of x. Do you understand this? For each x, you're gonna get a y. So in this case, you're gonna get a y cubed. So still a function. So now let's take the derivative with respect of x. So in this case, you should recognize that a composition is taking place. So we need to use chain rule. So what's the derivative in this case? What is it? So this is 3y squared times y prime. So in other words, if you remember the way that we wrote the little chains last time, what would be the chain that we have here? What's the outside function? X cubed. And what's the inside function? Y. And just use the chain rule. Okay? So 3y squared times y prime. Good. How about, or you can write dy dx, however you want.
So number 2 would be.
How about number 2? Say that again?
3x.
Just 3x?
No, times x prime.
Okay, so it's first one. It's 3x squared.
Yes.
But you said 3x.
Yeah.
So remember, power rule means bring this guy down and subtract 1 from the exponent. Yes?
Yes.
Okay. So this would be 3x squared. Now, you could say times x prime, but what is x prime? It's just 1, so we don't write it. In other words, here the derivative with respect of x. Here you have the formula, the function of x, so it's your usual derivative. Okay? You see the difference between number 2 and number 1? Okay, chain rule is not needed here. You can do it if you want, it's just that the x prime is just 1. Okay? All right. How about number 3? This is a sum. What do you know about the derivative of a sum? It's the sum of the derivatives, right? So let's see, I'm going to do this one slowly. So this would be the derivative of x plus the derivative of 3y. Do you understand this? The derivative of the sum is the sum of the derivative. What's the derivative with respect of x? 1 plus, and what's the derivative of 3 times y? You may, but that's like killing an ant with a rock. Let it go. Don't kill this. Let it go. The constant multiple, right? So you can, you can do product rule, but here this constant multiple, just bring the 3 out, right? And then the derivative of y is y prime. We don't know what y is, so we leave it like that. 3 times the derivative of y. Do you understand this? So you can do product rule if you want, but typically in situations like this, we don't. 3 times y prime. Questions? Remember, just keep in mind that y is a function of x. That's all you have to think about. But you don't know what it is. So whenever you need to take the derivative, just put y prime or dy dx. Okay? How about number 4? What do we do here? Now here we use product rule. Why? Because we have a product of 2 functions, right? This is the function x times the function y squared, whatever that is. You understand this? So here we need to use product rule. Okay. Who can tell me what the answer would be? 1 times
2y.
No, that's not what the product rule says.
2xy minus y.
No. What does the product rule says?
F prime and g.
Okay, what's g here?
Y squared.
So then y squared, right? Okay, what else? Plus x
Plus 2y.
times
2y.
just 2y.
Times y prime.
So 2y times y prime. So let's explain this again. So again, throw rule. Derivative of the first, that's 1, right? Times the second function plus first function times the derivative of the second. Now, what's the derivative of y squared? Here we have to use a little chain rule, just like what we did above with the y cube, right? So what is it? 2y times y prime, the derivative of the inside. Do you understand this? I mean, whenever you're taking derivative of something like this, that is implicit, that you don't know what y is, you have to have a y prime as a result in your derivative. If you don't have a y prime, you did something wrong. Okay? That's something that you can use, I guess, to make sure that what you're writing makes a little bit sense. So product rule. So here, this is your f, if you will. This is your f, and this is your g. Okay? So this guy right here is f prime times g, and then plus f times g prime. Do you understand this? Now we can put this together to do the last example that we had above. Now, solve example number 3 above. Okay, so it was number 3. Let's go ahead and let's find y prime. So x squared, number 3 above was x squared minus 2y cubed plus 4y equals 2, right? Okay, so here is the idea. How do we use these techniques or these ideas that we have explored now? How do we use it to find y prime? Well, it's an equation, meaning the left-hand side equals the right-hand side, right? If we find the derivative of the left, that has to be the same as the derivative of the right. If the two things are equal, the derivative better be the same. Do you understand? So that's what you do. You go ahead, once you have something like this, apply derivative on both sides. So now you do derivative of the left side, and that's going to be equal to the derivative with respect of x of the right side. Questions? Do you understand this? Now, the left side is an exercise like the ones that we have been doing. The right side is also an exercise. What's going to happen is that when you compute this, you're going to have another equation, right? Because the equal sign, another equation, and there will be y primes in it. Then what you do is solve for y prime. Okay? If you cannot solve for y prime, sometimes you cannot solve for y prime, you leave it like that, and then we say it's an implicit form. Okay? But typically you can solve for y prime. So let's do it. Let's see, let's focus on the left side. We're going to use here the same ideas that we did above. So here we have 3 terms. So when you take the derivative, we just combine the derivative of the 3 terms, right? So let's do it. Derivative of x squared, 2x, minus. Now what's the derivative of 2y cubed? Very good. That's 6y squared times y prime. Does everybody understand the y prime? Okay. Plus, what's the derivative of 4y? Good. 4y prime equals derivative of 2? 0. Did you understand this? Now, solve for y prime. Okay? So now here you can solve for y prime. So I'm just going to bring, let's see, I'm going to leave 2x over here. I'm going to bring this guy to the right-hand side just because I want to have positive things. And then factor out y prime. And then divide, right? I'm going to go ahead and I'm going to divide this expression. So we get that y prime equals 2x over 6y squared minus 4. And if you want, you can divide top and bottom by 2. So take out 2. Let's cancel. So we get y prime equals x over 3y squared minus 2. And here we have y prime. You cannot expect to have a nice formula with only x's because we don't know what y is. Why should you know what y prime is? But it's in terms of x and y, okay? So you're gonna say in the examples, remember, typically, why do you want derivative? Because you want to find the slope at a point, right? But when I give you the point, and in the previous sections, you only needed to know the x, because that's all you plug in, because you always had explicit functions. But now you need the full data. If you want to know the slope at a given point, you need the x, but you also need the y. Because you put your x, your y, and you get the slope. Do you understand what I'm saying? So here you're going to need both x and y. Remember, we don't know the formula for y, but once I give you an x, you should be able to have a value for y, because after all, y is a function of x. You put it here and you get the slope. All right. Questions? Did you understand this example? Okay, so let's do the circle one. So let's see, you do it. So x squared plus y squared equals 1. Find y prime. Anybody has an answer? What is it?
I got negative x over y.
So y prime equals negative x over y. Everybody getting the same thing? Okay, so let's see, let's quickly inspect this. So for example, we know this is a circle, right? Who can tell me what are the points at which we have horizontal tangent lines for this circle?
Negative x equals 0 and y is negative 1.
Exactly, so at the point 0, 1, 0, negative 1, yes? That's what we have for horizontal tangent lines. What does that mean about derivative? What are we expecting to have for the derivative at those points? 0, right? What does it mean to have a horizontal tangent line? Derivative is 0, right? When is this derivative 0? When is a fraction 0? When you have a fraction, when is a fraction 0? When the numerator is 0, right? So this fraction is 0 whenever x is 0. And when x is 0, the two possibilities for y are plus or minus 1, right? So this is telling us what's supposed to happen. Now, when is this derivative undefined? And y is 0. That means if you were taking the limit and so on, because this is a fraction, because you have a 0 in the bottom, you're going to be getting an infinity, right? So what are we expecting to happen when y is 0? Vertical tangent lines. Is that the case for the circle? When y is 0, you have the point 1, 0 and negative 1, 0, right? What's the tangent line at those points? Vertical lines. And here we're just playing with this formula to see if it's really giving us information about the circle. Okay? So as you can see, this is a nice package that has the information that you need. If you want to know the slope at any other point, well, you need to know the point, so you need to know x and y. Put it here, and you get your slope. Okay? So how do we find this? Just take derivative on both sides, right? Take derivative on both sides. And then when we take the derivative, we get 2x plus 2y times y prime equals to 0, right? So let me bring this down a little bit. Then solving for y prime, we get negative 2x over 2y. The 2's cancel, and then you get your negative x over 1. Okay? All right, good. Question. This is called implicit differentiation. You see, we were able to come up with an expression for y prime without really knowing what y was. And the secret is that we use chain rule. It's not a problem. Okay? All right, so let me write more examples here. Let's see. So we have sine of x plus y equals x. Then find dy dx and evaluate it at the point 0, 0. So notice that when x is 0, right, then you get the equation sine of y equals 0, okay? And if you make y equals 0, then that works because sine of 0 is 0, right? So if you put 0, 0 here, you're gonna get sine of 0, which is just 0. So the point is, this is a point on the graph of this equation. Okay. So find y prime evaluated at that point. In other words, I want to know whatever the graph of this equation is. I want to know the slope at the origin. What's the slope at 0, 0? That's really what this is asking to do. So find the equation of the tangent line to the graph of x squared plus 4y squared equals 4. What curve is this?
Is that a circle?
No, for to be a circle, these two guys have to be the same. The coefficient have to be the same. What curve is this? It's an ellipse. Okay? So circles are special cases of an ellipse. Ellipse is a more general figure. Okay? So this is an ellipse. So find the equation of the tangent line to the graph of this ellipse at the point square root of 2, comma, -1 over square root of 2. So, for example, just to remind, okay, once we get there, then I give you a picture. Actually, let me give you the story now. So notice that you can rewrite this as divide everything by 4, and hopefully it's gonna look more familiar to you. So you can write as x squared over 4 plus y squared over 1 equals 1. This is the standard form. This is how you know that you have an ellipse, where you have denominators here, but they're not the same numbers. Okay? So because this is the biggest denominator, that means that the major axis is the x-axis. The center is the origin, and the major axis is the x-axis. Because when you have an ellipse, it can look like this or like this. And the major axis is the longer axis. In this case, we have a picture like this one. Because the biggest number is on the x. So it looks like that. If the 4 was here, then it would look like this. If the 4 was with the y squared, it would look like this. Okay? The major axis is the y-axis. So this ellipse, you don't need to do this question, you don't need to graph it, but this is so you have a visualization of what you're doing. So let's look at the ellipse. And to graph this ellipse, we know the major axis is the x-axis, so the vertex are, remember this is 2 squared, so that means you're going to go 2 this way, 2 this way, and then this is 1 square, so you go 1 this way, 1 this way. Okay, those are your 4 vertices. So that's 2, that's -2, 1, -1. This is what we call a is equal to 2 and b is equal to 1. This is a squared, this is b squared. The case of a circle is when a and b are equal to each other. Okay, you have the same denominator, and then you have a nice round thing. So this is how it looks, and then in this case, the point that we're interested in is square root of 2, comma, -1 or square root of 2. So that point is somewhere in here. The point somewhere here. Let's call it P. So this is what the point P is. And then what I'm asking you is find the equation of this line. This is the question, okay? To find the equation of this line. Given this picture, find the equation of this line. All right? Now, for example, if you want to avoid implicit differentiation, if you refuse to learn implicit differentiation, you shouldn't, because then you cannot do problems like the previous one, like example 3, right? But let's say that you refuse to use implicit differentiation whenever possible, because here you could solve for y, right? Then the problem is that you have to solve for y, you're going to get 2 equations, the positive and the negative. You need to understand that you have to pick the negative version, because look where the point is that we want to find the slope. It's on the bottom part of the ellipse, right? So that point belongs to the negative version of the ellipse. That's when y is negative. So you will need to pick that second formula with the negative, and then you can use your derivative, using the rules to find the slope and so on, okay? But keep in mind that that's not always good because sometimes you can just cannot solve for y. Okay. So the good thing about implicit differentiation is no need to solve for y, no need to even care about the picture. You can just work with the formula, with the equation right away. Okay. All right, but it's always good, if possible, to have a visualization of what you're doing. Okay, so that was that example. I mean, that I want you to do. And then let's do this one. So find the second derivative for the notation, that's dy dx squared, which is just y double prime, okay? For a circle. So for x squared plus y squared equals 25. Okay, so here you have 3 examples. Start working on it. I'm gonna take attendance and so on. And then understand how to do number 1?
Yes.
Okay, so let's do it. So we have solution sine of x plus y equals x. Okay, and remember, our job is to find dy dx at the point 0, 0. So this is typically how, if you use Leibniz, so if you use Leibniz notation, this is how we write evaluating at a point. So we put dy dx, draw a line like this, and then down here you give me the values that you want for x and y, and then you plug it. Okay. All right. So what's the first step? What's the first step? Take derivative on both sides, right? So first step is take derivative of the left equals derivative of the right. And remember, this is derivative with respect of x. Okay? All right. So what's the derivative of the left? Cosine of x plus y. That's it? What's the inside function? I mean, do you see the composition here? What's the inside function? X plus y. So times derivative of the inside. What's the derivative of the inside?
X.
1 plus y prime. Remember, the derivative of x is 1. Do you guys understand what's going on here? We have a composition. What's the outside function? Sine. What's the inside function? X plus y. So when you take derivative, is derivative of the outside, okay, cosine, plug in the inside, times derivative of the inside. What's the derivative of the inside? 1 plus y prime. Do you understand this? Okay. Equals, what's the derivative of the right hand side? 1. Okay. Now what do we do? So we solve for y prime, right? Now we just isolate this guy, this y prime. Now it's algebra, what we need to do. So let's see. Okay, so I'm going to divide. So we get 1 plus y prime equals 1 over cosine. What's a nice way of writing 1 over cosine? Secant. So we get that y prime is secant of x plus y minus 1. Do you understand this? If you don't like the secant, you can leave it as 1 over cosine. Okay? So this is the derivative. Questions? Okay, now what is it that we need to do? So remember, what was the question? The question was find the derivative and evaluate it at the point 0, 0. So now that we have the derivative, we need to do is plug in 0, 0. So that means plug in 0 for x, 0 for y. And plug in. So this is y prime. And then dy dx evaluated at 0, 0 is secant of 0 plus 0 minus 1. So that's secant of 0 minus 1. What's secant of 0? Remember, secant is 1 over cosine. So what's cosine of 0? 1. So secant of 0 is 1 over 1. So it's just 1, right? So this 1 minus 1, 0. So that means that we have a horizontal tangent line to this curve, right? Whatever the curve or sine of x plus y equal x, however it looks like at the origin, we have a horizontal tangent line. That's what we have found. Questions? For example, let's see. Quickly, without using too much time. You know, it's always good to have a visualization of what we're doing whenever possible. Okay. So sine of x plus y equals x. So this is that curve, sine of x plus y equal x. I mean, it's not a function, but if you look at pieces of it, and let's say from here to here, right, this portion from here, that's a function right there. Okay, it passes the vertical line test. So you can take pieces of that curve and make it a function. Why am I taking that piece and not any other piece? Well, because we're interested in the point 0, 0, right? So we need to look at a piece of the curve that contains the point 0, 0. So it will be something like this. Okay. All right. And what we just found is the line y equals 0 is a horizontal tangent line. And as you can see, indeed, and this is nice smooth function here. So when you get close to the origin, your secant lines, they become the x-axis. Okay. Okay. Again, you don't need to know what the graph is, but after the fact, we can do this to really visualize what we just did. Okay. Let's continue. Okay, so that was number 1. Questions? Right? So now let's do number 2. So number 2 is a similar story. We basically have to do the same procedure. We need to come up with a number, right? When you plug in the point, what would that number represent? The slope. Then what do you do with that slope? Use the slope on the point to find the equation of the line, because the original question is find the equation of the tangent line, right? So your answer has to be y equals mx plus b. All right. All right. So for number 2, remember that we have, what was the equation? X squared plus 4y squared equals 4, and the point P was square root 2 comma negative 1 over square root 2. So what do we need? So we need the slope. And what else? And we also need a point. Remember, the question is find the equation of a line. What do you need to find the equation of a line? You need a slope, you need a point. Do we have a point? Yes, we do. So it's right here. Do we know the slope? We don't. So our job is to find it. Okay? So to answer the question, we're going to pause here. We're going to find the slope. Then once we find it, we come back and finish writing the equation. Yes? All right. So let's find the slope. Finding m. Because as you know, what is m? By the way, how can we figure out m? So that means find dy dx, whatever it is, and plug in the point, right? And evaluate it at the point square root of 2, comma, negative 1 over square root of 2. Okay? So that's what it means to find the slope. So to answer the question, we need to come up with that number. Okay, so of course, it should be clear. I mean, it's easier to do this using implicit differentiation. In this case, you could solve for y, but then it's, you have to be careful because you have to take the negative version because of the position of the point, and then use the formulas there. but that's too troublesome. It's easier to just use implicit differentiation. Okay, so let's do it. So we're applying derivative on both sides, right? I'm going to apply derivative with respect of x to the entire equation. What do we get on the left?
2x
2x.
plus 8y times y prime
Good.
equals 0.
Equals 0. Everybody agree? So what's y prime? Let's see. Let's just solve here. So what is it?
Negative 2x
Negative 2x
or ay.
over ay. Everybody okay so far? Which we can simplify it as negative x over 4y. Everybody following this? Now, okay, that's the derivative, but remember, that's not what we want. What do we want? The value of this at the point. We need to come up with a number because we're looking for a slope. So, what is m? It would be dy dx evaluated at this point. In other words, for x, you put a square root of 2. For y, you put negative 1 over the square root of 2. So that would be negative square root of 2 over 4 times negative 1 over square root of 2. So x, I put square root of 2. Y, I put negative 1 over square root of 2. Do you understand this? Simplify. So these two negatives, they cancel each other, and this square root of 2, it comes to the top, right? Multiplying with the other square root of 2, giving you a 2. So this is 2 over 4, or 1/2. So our slope is 1/2, and notice that it's consistent with what we're expecting. We were expecting a positive slope because look at the picture. So if you get a negative number, something's wrong because we're expecting a line that looks like this. Okay. All right. So the slope is 1/2. So let me just begin here. So m is equal to 1/2, and the point is square root of 2, comma, negative 1 over square root of 2. So now I'm going to use the Points law formula. Remember, y minus y1 equals n times x minus x1. Plug in and we get our equation. So it will be y plus 1 over square root of 2 equals 1/2 x minus square root of 2. So y is going to be 1/2 x minus square root of 2 over 2 minus 1 over the square root of 2. These two things are the same, right? If you rationalize this, you get square root of 2 over 2. So you're basically subtracting two things that are, adding two things that are the same, but they're both negative. So it's twice this. So you get square root of 2 minus square root of 2 here. Okay? So you see what I'm saying? I'm going to factor out a negative. I'm going to write the square root of 2 plus square root of 2 over 2, right? I rationalize this one. And then when you combine, you get 2 square root of 2 over 2. The 2's cancel out. Okay? So do it however you want. At the end, you need to get this answer. Okay. Questions? So let me ask again. Do you understand how to find the equation of a line once you know the point of the slope? Because you're going to be doing this next week on the exam. This equation like this is going to come up. Do you know how to find the equation of a line? Yes? Okay, good. So this last part should be fine. So I guess the complicated part, if you will, is to find the slope. Or it's not complicated, but the new part is to find the slope. Questions on that? Do you understand how to find the slope? Is it clear why we use implicit differentiation? Okay, good. Right. Okay. So then let's do the last one. So let's find the second derivative of this circle. 3. We have x squared plus y squared equals 25. And then our job is to find y double prime. So, what do you think the strategy here is? So we find the first derivative, and then we find the derivative again. Now, you need to understand that the first derivative will be an expression involving both x and y. So when you take derivative again, you still need to use implicit differentiation. Okay? Sometimes it's easier, as you're gonna see here. For example, this is a circle. Typically with circles, the same sort of thing happens. So let's look at the one that we have from before. You see over here, when we find the derivative of this circle, because the question was just find y prime, you solve for y prime, of course, but then you get a fraction. If now here I want to find y double prime, what do I need to do? You need to take the derivative of the right hand side, and you will need to do a quotient rule. Okay? Nothing wrong with that, but since the target is y double prime, what you could do is, in this step right here, right, you already have your y prime, what you can do is take the derivative again, and the y double prime is going to pop up, but then the only thing is that instead of a quotient, you will do a little product rule. Okay. I personally prefer to do product rules than quotient rules. Okay, so I'm going to be doing that. Nothing wrong with going up to here and then using quotient rule, but if you can avoid it, why not? Okay, so that's what you're going to see me doing. Anyway, you're going to see that there is value in finding this expression. We're going to do it, but as the idea. Okay, so we want the y double prime, but first we need y prime. So we take derivative. On both sides. That gives us 2x plus 2y times y prime equals 0. Yes? And before we proceed, and we can go ahead and divide everything by 2 just to get rid of all of those 2's in there. Okay? So I'm going to divide everything by 2. So we get x plus y times y prime is equal to 0. Again, at this point, you can solve for y prime, because it's simple enough. It's good to notice here that this means that y prime equals negative x over y. Yes? And if you wanted to, you could go ahead and find y double prime right there. Okay. But instead of doing that, I'm going to just keep taking the derivative here because I prefer to use product rule. That's what I'm going to do. Okay, so now I'm going to take derivative on both sides once again. And I'm going to get 1 plus, now what do we do with this derivative? How do we take the derivative of this? Product rule. So everybody understand this? There is a product of 2 functions here. Okay, derivative of the first. What's the first function? What is it? So the first function is y. So what's the derivative? Y prime. Y prime times the second function. What's the second function? Y prime. Plus the first function times derivative of the second function. What's the second function? This is y prime, so derivative is y double prime. Do you understand this? Equals 0. And now solve for y double prime. So I'm just going to write this as y prime squared plus y times y double prime. Now we can solve. So y double prime is going to be negative 1 minus y prime squared
over y.
all over y. Do you understand this? Let me see. We're not done here, but let's say.
Could you do it the other way?
Yeah, I'm gonna do it the other way. But first, I want to show you something else. Actually, okay, let me just do it the other way. So alternative. So alternative would be, okay, you solve for y prime, and then you take the derivative, right? So y double prime equals the derivative of this. Okay, so it would be derivative of the top, negative 1 times the bottom, minus the top function times derivative of the bottom divided by the bottom function squared, right? So let's see, what is this? So this is a positive, so we get -1 plus x times y prime over y squared. And okay, so let's convince ourselves that what we have here is exactly the same thing as what's in here before I proceed. Okay, so here's what I'm going to do. I'm going to remember, these are implicit expressions. Okay, so I'm going to go ahead and I'm going to factor out y. So you see that the two things are the same. So I'm going to factor out y on top. So it will be a -1 plus, yes, plus. Now there is no y in the second term, so what do I need to do? If there is no y in the second term, divide by that, right? So I'm going to write it as x over y times y prime. Do you understand this so far? Again, what I'm doing here is just to show you that these two expressions, this one and this one, are equivalent. Okay? So we can simplify the y's. And then -1. Now here is the trick. What's x over y? Well, notice that y prime equals -x over y. Yes? Look at the top. Right here. Yes? So that means x over y equals -y prime. Yes? I'm going to put that in here. So -y prime times y prime. That becomes, so I don't have to write too much. That's y prime squared, right? And then over y. So you can see that these two expressions are the same. Okay? So it doesn't really matter what route you take. And now the point is, but it's good that we did this because now you see how we kind of use the fact that y prime was equal to -x over y to kind of work on this expression. That's typically what we do here. In other words, if this is your y double prime, we don't want to stop here. It's not good. Why is this not good? Because this expression depends on y. Sometimes it may depend on x. It turns out that here the x went away when we took derivative, but there could have been an x in here. And that's okay. We know that we don't have a formula for y, so we're expecting to have x and y's in our formula. But this is really painful because now we also need to know what y prime means before we get to know y double prime. Point is, if you can write y double prime in terms of x and y, you should do it. And in this case, we can because we know that y prime is -x over y. So typically what we do is we plug it in here. Okay? So when you find your derivative, you cannot get a nice formula because you didn't have an explicit expression for y. But the least that you can do is give me the answer only using x's and y's. I don't want to see y primes or all stuff in there. Okay? Because then if you want to find what's the value of the second derivative at some point, you need to know x, you need to know y, but then you also need to know the value of y prime. Okay? So just give me a function in terms of x and y, and that's what we're going to do. We're going to take this. We know what y prime is, so we plug it in here. Okay? So in other words, the problem is not done. At this step, it's not done. So that's -x over y squared over y. Everybody understand this? And now simplify. So that would be -1 minus x squared over y squared, because this other negative is killed by this squared. Okay? So this negative aside survives. Okay? There is no negative all over y. And now I'm just going to go ahead and multiply top and bottom by y squared to simplify the little fraction. So we obtain the y double prime equals -y squared minus x squared over y cubed. Yes? And if we didn't know any better, we will stop here. At least we have the condition that I require. We have y double prime in terms of x and y, so that's fine. But we can do more stuff here. There is something way nicer that we can do, just because this problem is special enough that can be done. if you see this, you may be willing to factor out a negative in the top. Why not? The two negatives. So if I factor out a negative, what do we get in the top? So I'm going to put the negative here in front of the fraction. What do we get in the top?
Y squared.
Plus x squared. So I'm going to write it as x squared plus y squared. Is that okay? Over y cubed. The reason why I'm saying this is because what do we know about x squared plus y squared? Well, okay, not necessarily 1, but it's 25, right? Because we started with that. We started with the circle, x squared plus y squared equals 25. So this is just negative 25 over y cubed. So this is way nicer than giving, first of all, this is nicer than giving this answer. And it's also nicer than giving this answer. Okay? So y double prime is negative 25 over y cubed. Which, by the way, now you need to find y, the third derivative, the fourth derivative, and so on. It's pretty easy because now it's just, well, okay, the third derivative is a power rule, chain rule. The fourth derivative, you have to use a bunch of rules and so on. But still, it's more manageable than before. Okay. Questions? So, there's some algebra involved in these steps, okay? So make sure that you look over this. But most of the time, you can clean up the expression in such a way that you get something nice. Mainly when you have circles and so on. Okay, but this is a standard procedure. When you find the second derivative, the y prime is going to pop up. Don't leave it like that. So remember that to get there, first you had an expression that would allow you to solve for y prime. Do it, because then you're going to plug in that formula into your final answer, so you can get your y prime and have everything in terms of x and y. Okay? All right. Questions? Yes?
If we don't simplify like all the way to the last step, like if we just stayed at x squared plus y squared over y cubed, would that be wrong on the test?
It depends on the question. So if I just ask you find the derivative and it's open-ended, for example, you stop here. And for example, if you stop there, I will take it away because that's not acceptable. I want to see only x's and y's. Okay? If you stop here, that's okay. But what if it was multiple choice? That's the option. So you have to be able to do this because if it's open-ended and you stop here, not a problem. Okay? But you have to be able to do this. Also, what if I had asked you for the third derivative? Nothing wrong with stopping here, but then you're going to have a harder time to find the third derivative. While over here, it would have been pretty simple. Okay? So it really depends how the question is asked. And in doubt, you ask me. Professor, look, I'm here. Am I supposed to continue, or is this good enough? And then I'll tell you. Yeah, I'm not going to tell you how to do it, but I'll tell you it's okay to stop or try to do something else. Okay? Or try to do more. All right. Are we okay with this? Okay. So that was implicit differentiation. So hopefully you see why I really need you to understand chain rule. Because basically this is chain rule left and right. Okay? But on a more subtle level. Like the composition is not the one that you're used to see. Because there are y's now, not just formulas. Okay. So now we know implicit differentiation and we know everything is chain rule here, really. We can use this idea to find the derivative of inverse functions. And here, this is quick, so let me just give you the full story. So recall, do you know what's an inverse function? Yes, it's given a function. First of all, for a function to have an inverse, it has to be 1-to-1. Okay? But given a function that's 1-to-1, then it has an inverse. And what's the inverse? It's another function whose job is to undo what the original function does. Okay? So whatever the output of this function is, then that will become the input of the inverse, and the output of the inverse is the input of the original function. So it kind of reverses the process. So recall inverse functions So I'm just gonna illustrate this with a picture. So suppose that f is a one-to-one function. You know what one-to-one is? So two different inputs will always give you two different outputs. Okay? For example, x squared is not one-to-one because you can plug in 1 or -1, different inputs, but what output do you get as a result? You get the same thing, you get 1, right? So x squared is not a one-to-one function. Okay? X cubed is one-to-one. Okay? All right, so suppose f is a one-to-one function, then we can think of this picture. Remember, functions are like machines. This is your function f. X comes in as an input, and then your output, which is y, we call it f of x, right? Whatever the output is. Then the inverse of f, so this is the function f. Then over here, I can put another machine, which we call it f inverse. Okay, this is the notation that we use. Now, this doesn't mean 1 over f. This is the notation for f inverse, the inverse function. And the job of this blue function, you can call it another name, g or whatever. The job of this function is to take this output. When this output becomes the input, it gives you back this guy. Okay, it recovers the original input. So when you feed this into the inverse, what you get back is, by the way, here you can see that this is a composition, right? F inverse of f of x, and this is x. In other words, you have your function f, the inverse is a function so that when you feed in the output of f, the output of your inverse is the original input that your f had, okay? So when you feed in the y, it's going to give you the x. Basically, that's what's going on. And this right here is the definition. So two functions are said to be inverse of each other if when you take the composition, you get back x, the original input. They cancel each other out, right? Like the exponential and the logarithm, they cancel each other. The x squared and the square root, they cancel each other. But I say square in quotation mark, remember, it's not x squared on the entire domain. You have to restrict it from 0 to infinity. So you have a one-to-one function, okay? And the x cubed and the cube root, they cancel each other. Okay, so this is what we mean by canceling each other. Here you can see that both canceling and you get back whatever was here. Okay, so that's the definition. So the definition is the inverse of f. So f is a one-to-one function. The inverse of f, denoted like f inverse, is a function so that when you do the composition, this happens, and the other way around as well. They cancel each other, nothing matters in the order, okay? Because what this is telling me is that then the inverse of the inverse is also the original function, okay? That's what this is saying. So that's what it means to be an inverse function. Now, as you can see, if you want to find out the derivative of an inverse, we can actually express the derivative of the inverse in terms of the derivative of f using chain rule. Because it's a composition, we can take advantage of that. Okay? So the question that we want is how to find the derivative of the inverse function in terms of the derivative of the original function. Okay? And it should be clear what to do, right? So right here we have this composition. We can set up this composition equal to x, take the derivative on both sides. On the left we use chain rule, on the right we're going to have 1, and then we solve. Okay? Alright, so note, we know that f inverse of f of x is equal to x, take the derivative on both sides. Now, if it confuses you, and I can call f inverse g. So let f inverse of x, let's call it a new function g. So really what we have here is the derivative with respect of x of g of f of x. Okay? Let's see. Let's do the derivative on the left. How do we find this derivative? Do you see that a composition is taking place here? How do we find this composition? Chain rule. So what do? Derivative of the outside. What's the outside function? G. It will be g prime of, plug in the inside function. Here f and g is a switch of what you usually used to see, but it doesn't matter, right? G prime evaluated at f times f prime. Okay, that's the derivative of the left, equals what derivative of x? 1. Do you understand this? And now we can solve for, remember, we want to know what's f prime of x, so we can solve for this. So g prime of f of x equals 1 over f prime of x. Do you understand this so far? Of course, this is assuming, here we need to make a note here. If the derivative of f prime is different than 0, then we can write this line. Okay, so this only makes sense if the derivative is different than 0. All right, so let's see. So now I'm going to put what g is. So g is f inverse. So what this is telling me is that the derivative of f inverse, let's see, how do I write this down? So this would be f inverse because it's gonna look super weird. I'm gonna call this y. Okay. Remember, y equals f of x. So y equals f of x. Okay. So that's y. So what we got here is that y prime, g prime of y equals 1 over f prime of x. Now, this y is the y of f, and this is the x of f, right? But if I want to write this now in terms of the inverse, because g prime is really the inverse, right? What do you know about the input? What's the x of the inverse? Is the y of the original function. Do you understand this? Remember, what the inverse does is it flips x and y. If you think about college algebra, when you were finding the equation of the inverse, what do? You have your formula for f, and then you switch x and y, and then you solve for y, right? So the y becomes an x, and the x becomes a y. So if instead of this, I want to write here f inverse, then I could write x in here, but then I have to put a y here, okay? But you need to understand I'm switching things, okay? Remember, g is just f inverse. But what I want you to know is that this x that I'm writing here, which is the same as this x, is really the y from above, right? Because it's the input of the inverse. So that means that the derivative, so f inverse, the derivative of f inverse of x is going to be equal to 1 over f prime of y. Remember, now this is the x of the inverse, and this is the y of the inverse. The y of the inverse is the x of f. The things are switched, okay? So I'm just switching x and y. That's basically what I'm doing. Because when you pass from a function to the inverse, you have to switch x and y. So finally I'm doing this because now y equals f of x. So this is the theorem. If you want to find the derivative of the inverse at some value, this is 1 over derivative of f evaluated at f of x. Okay, so this is the formula for f inverse prime in terms of f prime. And this, of course, this formula is valid as long as the derivative is different than 0, derivative of f. Otherwise, you're dividing here by 0. Okay? Okay. All right, so questions on this formula. We're going to do a little example now. So basically what this is telling you is that if you want to find the derivative of the inverse function, just find the derivative of f. Now, problem here is that you need to understand that what goes here is the y of the x given here to you. Okay? So for the original function, this x is really your y, and the value that you have here is the original input. So, let me see how, because here this could look a little bit confusing. Hold on. So, what is y? So we know that y equals f of x. We want to make sure that we don't do anything, because I don't want to freely switch things around. So this x here is the x of f, and this y is the y of f. Y equal f of x. So certainly this would be f inverse prime of f of x. Yes. And this is f prime of x. It's right here where I have to make the change. So if y equals f of x, then that means that x is f inverse of y, right? So if I apply the inverse function to y, then I'm gonna get back the original input that was x. So we're gonna stick that in here. I still have the same thing as before. Okay, so instead of an x, I kept my y here. I just replaced g by f inverse, because g is equal to f inverse, and then this y is still here. And then all I did was I changed this x by f inverse of y, because if y equals f of x, then x is f inverse of y. Now this is when I'm going to relabel things, because relabel things. Now this is the same variable, right? So this is y, this is y. Remember, this y is the output of f, but the output of f is the input of the inverse. So if I put x here, then it will be, so here all I did was just relabel y with x, because typically we want x to be the input, okay? But you need to understand that when we're talking about the inverse, your input is the OY. So if I put an x here, you need to understand that this x is the OY. But it looks weird like that, so that's why I want to write it in terms of x. Okay? So this is more friendly. So the derivative of the inverse evaluated at some x equals 1 over the derivative of f evaluated at the inverse function. Okay? So this is the y that we have. This is y, which is this one. Okay? Okay. So let's see. Questions? No? Let me just give you one example, and then we go. So let's see. Let's say that you want to find the derivative of inverse tangent. So find the derivative of the inverse tangent function. Okay? So if you want to find the derivative of the inverse tangent function using this formula, okay, then that means that we need to know what is f, right? So this is the inverse tangent. So what's the function f if you want to use this formula? So that's the inverse function. So f is tangent, right? So to use this formula, you need to understand that our f of x is tangent, and therefore the inverse function is the arctangent or inverse tangent. Yes? Okay, let's plug it into the formula. So the derivative of the inverse tangent, and next time I'm going to show you an alternative way, which is what I prefer to find the derivative of inverse function. But you need to know this formula, so let me just give it to you. So that means that the derivative of the inverse tangent is going to be equal to the derivative of f prime, so that would be, so it's going to be 1 over f prime evaluated at f inverse. So f inverse would be inverse tangent of x, right? Now, what is f prime? If f of x equals tangent of x, what is f prime? Secant squared. So let me write it down here. So remember, if f of x is tangent, then f prime is secant squared. So then this is going to be equal to 1 over secant squared of inverse tangent of x. So now the question is, how do you simplify this? What's secant of inverse tangent? This is an exercise from 3. Do you remember how to do this? So I'm going to come back here. So what is secant of inverse tangent of x? Do you know how to simplify this? The whole point here, the idea here is to understand that this is an angle, right? When you do inverse tangent of something, this is an angle, and then you're doing secant of that angle. So this angle, it has a name. Let's call it y or theta, whatever you want, right? But then that means that y equals inverse tangent of x. So if I do tangent of y, what do you get? What's tangent of y? This is just x, right? They cancel each other. So this allows me now to draw a triangle. So you can think of this as x over 1, right? Because x equals x over 1. So this allows me to draw a triangle in which the angle here is y, tangent of y, so y is an angle, right? And remember, tangent is opposite over adjacent, right? So this is a triangle in which this is x and this one is 1. Do you understand this? What's the hypotenuse of this triangle? You did this in trigonometry last semester. What's the hypotenuse of the hypotenuse of this triangle? The Pythagorean theorem. Square root of 1 minus x squared. Yes? A squared plus b squared equals c squared. I'm trying to do this quick, but you're not letting me do it quick. Do you remember the Pythagorean theorem? The sum of the legs squared equals the hypotenuse squared, right? And you solve for the hypotenuse. Okay, so you have the triangle. Now remember, this is y, so what we really want is secant of y. Okay. Use the triangle. What's secant? Remember, cosine is adjacent of hypotenuse, so secant is 1 over cosine, so it's hypotenuse over adjacent, right? So this equals square root of 1 minus x squared. Plus. Because this is the hypotenuse. So it's 1 squared plus x squared equals c squared, x squared, so it's a plus. Not a minus. It will be a minus if you have to solve for one of the legs. There's a 1. Okay, so secant of y is equal to 1 plus x squared. So we put it in there. So this is 1 over the square root of 1 plus x squared, because we have secant squared. So the square root cancels, and we get this. So derivative of inverse tangent
1 over
equals 1 over 1 plus x squared. Okay? I'm going to show you next time how to find this, but using this directly instead of having to use that formula. Okay? Because if you forget the formula, then and you could also get away from this if you use identities. You have to use identities. Another way to do that is to recognize what you know about secant squared. So recall secant squared of theta equals tangent squared of theta plus 1, right? So you could put here that this is your theta, tangent inverse. So this is the same thing as tangent squared of inverse tangent plus 1. And then the tangent with the inverse tangent, they cancel, and then you get your x squared. But then you have to remember the identity and all of that. Here we didn't need to use the identity. So I kind of prefer this. So next time I'm gonna explain this, and using this method we're gonna use inverse sine, inverse cosine, inverse secant, arcsecant, all of those. Okay.